So to start off with finding the equation for an electrical field for a straight conductor, um, you want to recognize that the force that the electrical field of the straight conductor is going to produce on this point here is going to be only x component, because if you look at, if this was the origin per se, and this is negative, this is positive because that's going up and that's going down, and you take this point here and this point here, which will have the same distance from this line, those would have their own y components, this one going down and this one going up. They would cancel each other out and only having x components. And same goes with points further up here and further down here of same distances, and those y components will cancel each other out, therefore only leaving the x component. So after you recognize that, you can start off by writing here ei to the x, or eix, is equal to kq over r squared times cosine theta, because we're only finding the x component, and then we can say that k is equal to 1 over 4 pi epsilon naught times, now in this situation we're using this specific piece of the rod, and we're finding its effect on this point here. So the charge in just this piece of the rod we're using as delta Q. So we're going to replace that there. So we're going to do delta Q over, and now r squared, this is going to be Ri, and Ri is here, and that's the radius between this piece of the rod we chose and to the point. And to find that, you can see that we have made a triangle here, so we're just going to do some Pythagorean theorem. So Ri is equal to the square root of d squared, which is this distance here, plus yi squared, which is this distance here. And so knowing that, we can then substitute that in, but because it's Ri squared, this will just go in as d squared plus y squared, or yi squared. And then cosine theta is just, we know cosine theta as adjacent over hypotenuse, and that's going to be the adjacent, which is d, over the hypotenuse of y. So d, or sorry, not hypotenuse of y, hypotenuse of Ri, and Ri we got here, so we're going to put that down here. So that's going to be the square root of d squared plus yi squared. And then that can go up here. So that's d squared, or just d, square root d squared plus yi squared. Alright, so now when we want to simplify all that, we go here, go e to the x is equal to 1 over 4 pi epsilon naught times d delta q over, forgot that parenthesis, d squared plus yi squared to the 3 halves, because this is just simply d squared plus yi squared to the 1 half. Here we're going to make some substitutions. If you remember, linear charge density is going to be lambda is equal to the charge, or Q, over L. And in our instance, we're going to be using delta Q over L, and L is going to be that little piece of the part of the rod we're going to be using. So we got Y, so it's going to be D times YI. And so we're going to be substituting this in for delta Q. So we get delta Q is equal to lambda times dyi, which is also equal to q over L, because lambda is equal to q over L here, times dyi. And then this is going to go in for delta q over here. And we get Ex is equal to, and we're going to combine it all here. So we got d q dy over 4 pi epsilon naught L, because you can't forget this L here, times d squared plus yi squared to the 3/2. Everything substituted in. We're going to start to integrate the function. So we're going to pull out all the constants. So dq over 4 pi epsilon naught here, and then we got dy over L times d squared plus y squared to the 3/2. And we're going to be integrating this from L over 2 from up here, L over 2 to negative L over 2. So now that we have this, this is where the tricky part comes in. We're going to try to integrate this right here. So we're going to use this shortcut, I guess you could say, which when you're trying to integrate something like that, it's going to be dx over a squared plus x squared to the 3/2. And then that's going to equal x over a squared square root of a squared plus x squared. So this is going to be what we have after we integrate it. So this is what we have now, this is what we have after. So afterwards, we got e to the x, or ex, equals dq over 4 pi epsilon naught, and then here we have, so it's going to be, so dx to x, so it's going to be y over a squared plus x squared to the 3/2. So it's going to be, so a squared, I did actually, now that I think of it, this is not going to be with this. This should be over here. My fault. So, so we got a squared. So a squared is d squared. So we got d squared. That's going to go out there. Root d squared again, because that's taking place of the a, plus y squared. And so that's going to be what we have afterwards. Now, so we got e to the x, or ex, keep doing that, dq over 4 pi epsilon, oh, this is a 3, that should be epsilon naught L, there. So in this situation, we're going to be substituting in L over 2 for all the y's we have in this here. So we got L over 2 d squared times d squared, and we're going to turn this into this all to the 1/2 instead of the root, plus L over 2 squared to the 1/2 minus, this might get in the way, a negative L over 2, because that's going to be the second part we have here, times d squared plus a negative L over 2 squared to the 1/2. Getting all in the way here. And then that's going to be in the box here. Alright, so now we get to cancel things out, or first we got to simplify that over here. So Ex is equal to dq over 4 pi epsilon naught L times, so this is going to be plus a positive, so that's just going to be L over d squared times d squared plus L over 2 squared to the 1/2, or yeah, to the 1/2. So now we can start to cancel terms out here. So these d's cancel, that, or one of them goes away, that cancels there, that L, and we end up with e to the x is equal to q over 4 pi epsilon naught times the square root of, or sorry, I forgot a d in here, epsilon naught d times the square root of d squared plus L over 2 squared Now, after we've gotten the equation for a straight conductor, finding the electric field for the straight conductor, we can now ask the question, what if the rod were infinite in length? So this brings an entire new equation. Well, it comes out with an entire new equation, but we can start with the equation we ended with for the electric field of a straight conductor. So we got this, we got the equation here, q over 4 pi epsilon naught d times the square root of d squared plus L over 2 squared. Now, we know that the linear charge density is equal to q over L. So q is equal to lambda, or the linear charge density, times L. So here, when we think of the rod being infinite in length, this could be so long that theoretically the distance between the rod and the point really won't affect the answer. So when it gets in such great length, this just doesn't matter anymore. So we can make that 0, making this the square root, so that's just going to be L over 2. So it's going to end up being 2q over 4 pi epsilon naught d L. And now, plugging this in for this, we get Ex is equal to 2 lambda, ooh, that was ugly, L over 4 pi epsilon naught d L. So That becomes a 2, L's cancel, and the final equation is going to be lambda over 2 pi epsilon naught d. And that's going to be, we just answered if